All right. Good morning, everybody from Germany. My name is Matthias Locherer. I'm from Cubert, a manufacturer of hyperspectral snapshot cameras looking like this. So our cameras actually have this size. Let me share my screen with you because I have prepared a presentation. So just a second. Oh, sorry. Just start in the beginning. So my presentation today is about video spectroscopy and biomedical applications and why our patented light field spectral imaging technology is a great idea for applications like that. But let me just start in the beginning. Cubert is a manufacturer of hyperspectral snapshot cameras, and snapshot means, according to conventional recording techniques, our cameras take this hyperspectral data cube in one single acquisition with one single data readout. We're on the market since 11 years now. Cubert was founded out of the Laser Institute of the University in Ulm. That's where we are located. Ulm is a city in southern Germany between Stuttgart and Munich. And what we nowadays offer is a bunch of off-the-shelf hyperspectral video cameras, but also very important to tell that we provide a lot of software solutions. So we have developed an entire spectral imaging software that serves for calibrating the cameras, recording images, and even real-time analyze potential. In the last years, also customized software solutions became more and more important. That's why we have developed a full software development kit, an SDK for system builders. What we also offer is product customization, meaning customers contact us telling us about their applications, and in certain cases we are able to develop prototypes exactly fitting to our customers' needs. Of course, we're also helping them with the application and integration support. It is important to say that I think with like with any new current technical company, we now employ more software engineers than optical engineers because software has become so much important in the meantime. I will tell you a little bit more about that in a few slides. Let's speak a little bit about our application fields. Where are hyperspectral cameras like these are used? Typically, in the moment, there are three major application fields. The first one is environmental monitoring, so classic remote sensing. Actually, this is where hyperspectral imaging is coming from. So it wasn't I think in the 1980s, when the geographers first used to work with a point spectrometer, pointed it to a leaf and tried to find out, do we see something interested in the reflected light of a leaf? Can we retrieve some information? And they found, yes, they could. They could find out about the vitality of vegetation, the water content, the chlorophyll content, which in agricultural context is directly related to nitrogen demand of plants. So this is important for fields like precision farming. So you know how to fertilize your agricultural fields. So this is still one of the major blocks where hyperspectral imaging is used. So in our case, UAV-based mapping, since the cameras have only this size, they're very suited to be mounted on a UAV and to fly fields, for instance. There are also some younger fields that become more and more important. That is industrial imaging, especially focusing on quality control, such as food quality. With such tiny cameras, you're able to determine some information. Example given, such as ripeness of fruits in the entire delivery chain. So food quality becomes more and more important, and we see increasing demands here as well. And last but not least, biomedical imaging, and this is also where I want to focus today. hyperspectral snapshot cameras are very suited to be used in the biomedical context for various applications. I will tell you a little bit more about this later. It's an ideal tool for clinical diagnosis and monitoring of diseases, for instance. Let's first speak about the necessity of hyperspectral imaging and why hyperspectral imaging is superior, of course, to classic blue RGB imaging and also multispectral imaging. On this slide, we just want to point out the advantages of hyperspectral imaging. You see here on the left-hand side some graphs of comparing a multispectral imaging system on the left-hand side, so this one, and a hyperspectral imaging system on the right-hand side. On the x-axis, typically we see this the wavelength of a certain spectral response. The y-axis just the intensity. It's just the schematics. But the main difference is, while in multispectral imaging you only have a distinct number of spectral bands, and typically those bands are broadbanded and you have gaps in between. In hyperspectral imaging you have very small bands and typically there are no gaps in between, meaning you have a continuous coverage of the entire spectrum. This, of course, provides much more information than multispectral imaging. And when we take a look at the right-hand side here, this is just a classification example of some kitchen herbs we used. We try to separate them automatically by using machine learning classification technique. We just see, compared to the multispectral setup on the left-hand side, a hyperspectral setup on the right-hand side provides much higher accuracy in retrieving information, because in the end we're not interested in retrieving a hyperspectral data cube that is very colorful. We are interested in the information that we can retrieve out of this data cube. Another advantage of hyperspectral setup is you can quickly identify critical spectral bands or channels, like we say. In this example, this shows how a hyperspectral setup can really detect the differences between oxygenated and deoxygenated blood, which is super important, for instance, in a surgery, to keep track on that. So with a multispectral system, you won't be able to see anything here. Second pillar of our technology is this snapshot advantage. What does that mean? Snapshot advantage means that our camera, compared to a classic scanning system, like I mentioned earlier, is taking the entire data cube at once. So what is a data cube? Typically, a hyperspectral camera produces, or with the data taken with a hyperspectral camera, produces a three-dimensional data cube. And while you have typically in the first two dimensions, that is in X and Y direction, you have the spatial information, like in a common image. In the third dimension, we find our spectral data. So we have lots of layers of the very same image, each time taken in a different wavelength. So this is what we call the data cube. And the data cube can be generated based on different sensors, like I say, classic push broom sensors, which align scanning devices, or snapshot systems like our devices. And snapshot means the entire data cube is read out at once. And this brings some advantages with it. You have a very speedy camera. This allows now true video capabilities, so you can work on a live data stream, which is not possible with a scanning device. And this also allows you to keep track with moving objects, so with dynamic applications. Furthermore, snapshot systems are very robust, like our camera here. They don't contain any moving parts in the camera, so they are, can easily handle vibrations and quick movements. Furthermore, hyperspectral snapshot cameras get smaller and smaller, so they can be used in any environment, either from surgery rooms up to greenhouses for measuring Brix content in tomatoes, meaning hyperspectral snapshot cameras can be used very versatile. There are a lot of different techniques on the market how to record hyperspectral image data. Just the most important example shown: Cubert light field hyperspectral imaging. This is what we do. This really allows true video spectroscopy. You have a high resolution data, but I'll speak about that later as well. A high light throughput, so leading to a very good signal to noise ratio. And this is, of course, time saving. Push broom, the classic approach. Here you definitely will find the highest spatial as well as spectral resolution. It's a technique that is also more than 40 years old now, still providing very accurate data. However, you have the advantage that you need to pre-process the data before you can work on a data cube, because it's scanning. So scanning means you either need to move your samples underneath the camera, like on a conveyor belt, or your camera needs to move above the ground, like from an aircraft, for instance. And there are also younger techniques like filter on chip, Fabry-Perot filters. That's kind of a similar approach. Here, different coatings or layers of Fabry-Perot filters are directly placed onto the sensor. But typically, this does not allow a true hyperspectral setup. Just an example given. So let's speak about our technology. Light field imaging, what is, or hyperspectral light field imaging? Let's first speak about the working principles of light field HSI. HSI, you will find it often means hyperspectral imaging. So light field imaging typically, or also called light field camera, is a planoptic camera. Compared to a classic camera like you have it in your iPhone, it does not only measure the intensity of light, it also gains information on the direction of the light. So we see where the light is coming from. And this is achieved by not having typically one camera lens, but having a whole array of camera lenses. And this principle allows to reconstruct really 3D information, or to refocus the image onto different planes. So this is where typically light field cameras are used. When we speak of a light field camera, this means that typically a micro lens array is placed on top of a CMOS sensor. And now we use this principle and add a third component, and that is a spectral filter. So what you see here is the schematics of Cubert cameras. We have three major components. That is a large CMOS sensor, and in case of the Ultras X20, which is the model I have right here, we use a 20 megapixel sensor. And on top of that, we place a micro lens array. And we are not interested in deriving three-dimensional information. We are interested in the spectral information. So we now add optical bandpass filters on top of each of the single lenses. So what is going to happen is the camera takes the very same image several times simultaneously, so at the very same time, using one sensor. And you see here the pure sensor readout of an example. And you just see how brightness and contrast in the images is varying. Then this due to the different optical bandpass filters. Now we only need to reconstruct the three-dimensional data cube, and there are running a bunch of correction routines. You have a parallax effect that needs to be corrected. Of course, if you have different positions, physical positions of lenses, and you're doing close-up measurements, meaning in a lab, for instance, each of the lenses has slightly different angles towards your samples. And we can see that. Let me go back. In this example, this schematic shows three camera lenses looking at two objects, a pyramid and a cube. And this is how it looks like. And you can imagine how this causes a parallax effect, like we have it with the human eye. And this needs to be corrected. our software is capable of doing that. Besides other correction routines like systematic errors, like the lens error, the dispersion, and so on, and also any light calibration techniques that are performed here as well. The parallax or this light field approach is also the reason why you cannot simply mount a common lens on top of the camera to get different field of views. But let me point out that a little bit later. Nice side effect of this approach is that it has a very high adaptability. So meaning if our customers are telling us we need a certain wavelength range to be covered, or we need a certain spectral resolution, which typically is defined by the full width half maximum given by the optical filters, is needed, and also with a certain spatial resolution, we can customize this approach very quickly. So we do a lot of rapid prototyping and, like I mentioned, develop solutions that exactly fit to our customers' requirements. And that is really nice. We can do that very quickly and adopt this principle. That is truly one of the advantages of this hyperspectral light field imaging. And typically what can be modified is the filter, the microlens array, and the sensor, besides other components, like, for instance, the connectors. In this case, the Ultra 620 is using a Gig E Vision Ethernet port. We can also use industrial standards if needed. That really depends on the requirements of the particular application. Another advantage of this approach is that it really comes with a very high quality. What you see here is the transmittance of the optical bandpass filters that are used in the Ultra 620, our major model with the 20 megapixel sensor. So on the y-axis, we see here the transmittance in percentage, and on the x-axis, this is the wavelength range our camera covers. So it starts in the ultraviolet at 350 nanometers and really is going through the entire visible range and covering the entire near infrared. Near infrared is not clearly defined, but typically you can say up to 1000 nanometer, this is near infrared. Everything after 1000 nanometers is known as shortwave infrared, typically going up to 2500 nanometers. Our basic cameras are limited to this wavelength range since we use silicon-based sensors, and silicon-based sensors are only sensitive in this range. So if you want to go to the sphere, the shortwave infrared, which we can do as well, you need different sensors, like, for instance, the Sony IMX990, combining different materials that are also sensitive in the shortwave infrared. In this case, let's speak about the X20 filters, as I said. And what you see here is that the transmittance of all optical filters that are used in the camera is very high. So typically more than almost every filter, more than 90%, except one, which is around 90% at 870 nanometers, which is absolutely awesome. And this setup has some advantage, because typically the full width half max, which defined somehow the spectral resolution, is increasing with higher wavelength in, for instance, prism-based setups. In our setup, this is it's constant 10 nanometers, which really allows now a true equidistant band setting in a very high quality, since we have an OD4 blocking, meaning we have less than 0.01% stray light effects on the camera. Let's speak about our cameras. So our product portfolio, we have developed several variations of this light field cameras. The first one was the Ultras S20, which used a linear variable filter. Now we use the X20 distinct filters. And what you see here is the lens array of the Ultras X20. So each of this is a tiny lens taking the very same image, and each lens has its own particular optical bandpass filter. One variation of this X20, for instance, is the X20 Plus, which is a dual sensor camera. You see it here, there's a second camera on top of it. Or the very tiny version, the Ultras 5, which is very versatile in usability. So typically, we make a separation between two product lines, the X line and the S line. The X line is describing really the premium product range. Here we use the largest sensors, the best filters, providing the largest wavelength range. While the Ultras S line is really developed for OEM applications, but also for biomedical applications. I will show you that in an example in a few minutes. First of all, we always speak of a hyperspectral camera. Let's be honest, that is not an accurate term. More accurate would be to speak about an imaging spectrometer, because that's what it is. And if we take a look about the spatial resolution of a data cube, this might not appear to be very high. 410 by 410 pixels is less than a VGA monitor's resolution. If you think about huge computer monitors in the 1990s, yet one have to consider 410 pixels each side means 170,000 pixels are taken at once, and 164 times. So we generate a lot of data in a very short amount of time. The wavelength range of the Ultras S line is more limited. It's 450 to 850 nanometers. We have less spectral bands, 51, a higher sampling rate, and also a lower resolution, as you can see here, but brings some other advantages, which I will show you. I don't want to go into detail of every component on this technical data sheet. If you have more questions to this, I'm really happy to answer any questions, and you can also find this information in the data sheet which are publicly available. So what we also provide, of course, one of the largest focus is UAV mapping, so remote sensing applications, which is why we have developed a gimbal for the very popular DJI model M300 RTK, which makes it very easy to integrate the cameras. You see here the X20 Plus mounted on that gimbal on UAVs with an integrated mini computer, all connected via DJI Skyport to the drone. So this makes it very easy to generate hyperspectral maps. And typically we use the X20 Plus model for that. And this means it's a dual sensor camera, like I said, combining the Ultras X20, which is the spectral camera with this resolution, and another panchromatic camera, just one band, but a very high resolution. And typically this high resolution data, by the way, this image shows a winter wheat field in Germany. You see here are the cars. And we use this panchromatic data, for instance, to generate pan-sharpened product. Pan-sharpening is an image fusion technique that has also been developed some decades ago to increase the spatial resolution of hyperspectral image data. And this provides much more details on the surfaces. You can see much better the heterogeneities. And typically this pan data is also used to calculate the mosaic for maps. So if you fly with a drone, you take a few hundred images, and the pan data is really helping the software, stitching software like Agisoft Metashape, for instance, or Pix4D, to calculate the mosaic, because in the end you want to have an entire map and not only single tiles. Let's speak about another model, the Ultras SR5, which is the Ultras 5 equipped with a relay lens. Why is this relay lens needed? As said, our cameras are light field, meaning we have a micro lens array, and you cannot just simply mount different lenses onto the camera. However, if you want to do that, and there are certain application fields where this is necessary, we have developed this relay lens adapter, which fits to any C-mount device. This could be a lens with different field of views, or really more complex optical devices like microscopes. endoscopes, or other inspection systems. The relay lens is transferring the image data on a two-dimensional plane, ensuring that each of the micro lenses in the camera can see the very same portion of the image. I will have a nice example of the relay lens in a few minutes. Then there's also a high frame rate becoming more and more important. The Ultras 5 HFR is a variation of the Ultras 5 that does now use a 10 gig Ethernet port to really read out the data very quickly. This allows a frame rate of 75 Hertz, meaning 75 data cubes at once. So for industrial processes, this is super important to have a very fast processing. Go with that. Let's just speak a little bit about our software. As said, the Cubert software suite brings a lot. First of all, you have the typical Windows-based software with the graphical user interface, the GUI, that is the Cubert Utils Touch, together with the core, which is the backend that does all the processing. We do not any processing on the camera. It's all done on the computer. Coming with a lot of features like live data stream and analysis mode. You can apply your own plugins, and you can export the data, of course, in typical file formats like NV and TIFF. The SDK that is really developed for system developers is based on C. We now have wrappers, very important, for Python, C++, and C#, and is available for Windows systems as well as for Linux systems like Ubuntu 20.04. So you can really embed this into your own software environment. A quick view on the graphical user interface. The touch is looking like this. So typically on the left-hand side, you have an image, while on the right-hand side, we see the spectral information of pixels I draw in the image. So I draw here a red box, and I get the spectral signal on the right-hand side of all pixels inside that box. Focusing a little bit on biomedical imaging, Cubert cameras are nowadays more and more used in different medical applications. And just example givens, a very important application is detecting Alzheimer's disease detection. And this is done with a very simple eye exam. So typically, Alzheimer is a form of dementia, and typically 1 of 3 humans at a certain level develops dementia. And 60% up to 80% of dementia cases are caused by Alzheimer's disease. And typically, to early monitor Alzheimer, there are already techniques, but they are very expensive, like the complicated PET scan. And together with our Canadian partner Redispec, we, or in particular, they have developed a method where they connect a hyperspectral camera from us with a fundus camera, performing a simple eye scan like at the eye doctor. And because hyperspectral imaging allows you to really detect some proteins that are helping to identify whether there's Alzheimer's disease accuracy or not. And current studies, are currently starting into a huge clinical study, predict 86% sensitivity with the 80% specificity. So this is a very promising approach. So this is, for instance, an image of the eye of a person, and this can be done very quickly to really achieve this information. Another application field is to use hyperspectral imaging for surgical guidance. The SNAPSHOT approach really allows to use the camera. You see here one of the testings with our partner, Hypervision Surgical, which are located in the UK and are connected to the King's College in London. They are really trying to develop surgical guidance using handheld hyperspectral images. Just easy example like the blood oxygenation, but there are so many more medical parameters that can be taken in this non-invasive, non-contact information gaining, which is used here. And a third example I would like to show you today is how hyperspectral imaging is used to diagnose melanoma on the skin. So this is also important that to track this or to monitor this at an early stage as soon as possible. And together with our partner, the DKFZ, which is the German Cancer Research Institute, we have developed a handheld and quick to use hyperspectral dermatoscope, which allows to provide hyperspectral data in real time and also apply already analysis methods, classification techniques, or anything that is using artificial intelligence, of course, machine learning techniques. And this hyperspectral device, the hyperspectral dermatoscope, I have currently here. So what you see here, this is actually the Ultras 5. It's just this size. And we have developed it together with an integrated light source that you can just put it onto the skin. And I would like to show you how easy it is to work with this device. So let me just skip that part and directly show you how easy it can be to use our cameras. So as I said, the graphical user interface is developed for Windows systems, which is why we have here the Cubert Utilist Touch, which is the GUI, and the core, which is the backend. And I will just show you the camera in action. I think it's easiest. So I start the touch, which also opening the core, and the touch, the core is immediately trying to connect to the camera. And after a few seconds, we got the message that the camera is online. So let's go back to the live view here. Let's enlarge it a little bit. And we got an image. And this is already a hyperspectral image. So let's have a quick view on the processing mode. We are in raw data mode, but at a certain level, we want to go to reflectance or at least spectral radiance. But first of all, we're starting in raw data. And when I draw a box like this, it gives me already the spectral response of all pixels inside that box. You see here the wavelength range, 450 to 850 nanometers. While on the y-axis you have the sensor count. It's a 12-bit system, so max value is 4095. And the error bars you see here is the standard deviation for each spectral band of the average pixels in this box. So let's draw another box like this, and we get the spectral response of this box here. However, it's uncalibrated, and so what I'm first going to do is I'm using a wide reference card like this, and I'm placing the dermatoscope for calibration purposes on this wide reference panel. So what we see now is that the data is totally oversaturated, meaning the integration time is way too high. So let's first have a quick view on the settings. We see here the integration time symbol, and the software starts with a default setting of 100 milliseconds. We don't need that. So let's use the auto exposure to find a much better value. And you see how it's decreasing, and also how the spectral response is going down and providing us with a not over-illuminated image. So I think 35 milliseconds is fine. Let's fix that here. And what I'm going to do is I'm doing a white referencing, and for taking the white, I'm going to average 3 images in a row, as well as for the dark. But let's first increase the frame rate, which is here. The default setting is also 1 Hertz. Let's say we want to have 5 Hertz to get a little bit more fluent illustration. And then I'm going clicking here on the white and taking the white accordingly. Once this button appears to be green, the software says it's good, let's go on. Secondly, I need to do a dark as well. For that, I'm going to deactivate the light source, measuring the dark current, which is a systematic error as well, deactivating it. And we now can change the processing mode to reflectance, and let's say RGB true color. So it's a 3-channel image now, not a preview image anymore. And of course, this provides us with a 100% reflectance signature based on our white target. However, what we also need to do is we need to do a distance calibration only one time due to the light field nature of the camera. And you see that here, that there is a huge distortion between different layers. And that is because of the parallax effect of the different lenses. So let's just do one calibration step here as well. I'm doing a distance calibration by taking a measurement. The software is taking an image, is performing a pattern recognition for each spectral band. So let's just do that. And is then aligning all the spectral bands accordingly and clear output. You have the white fields or black fields as well, without any distortions. By the way, you see a tiny oscillation in the spectral graphs. That is because of the 50 Hertz power supplies. The light source is not stabilized in the moment. So we have tiny variations in brightness, which is absolutely normal. And now, since the camera is calibrated, we can just use it, for instance, on my skin, looking like this. So you see, it's really like you can use it on the fly now. And you can also apply different different view modes. We just are in RGB true color. We can also go to colored infrared, highlighting one of the infrared bands, which is not so looking so much different for my skin. But you can also develop your own solutions. Let me show you that with a simple example. I have here one of our Cubert sweatshirts with the Cubert logo on it, and I'm going to show you how the Cubert logo is looking as seen from the hyperspectral dermatoscope in colored infrared. So it's actually looking like this. Again, going to RGB true color to give you a better idea. So typically, you can take a look at the spectral responses here from the black part, from the white part, as well as from the red part. And we can now just take a hyperspectral image by pressing this snapshot image. This is done now. Hyperspectral image is taken. But we can also, as said, apply, for instance, user plugins. One example is apply the NDVI, which is a vegetation index. However, it shows how you can just highlight features of the camera. Oh, it's turned around. Let me rotate the image a little bit. So this is better. So we see how this is working now. Hyperspectral imaging. Going back to the RGB true color. And also now, example given to how to take another image, and also from here, another image, how to apply analysis methods. I want to just show you how quick this can go. Putting this away. As said, we just have taken some data here available now. This is where our data has been stored. So we have a quick view file. We already have a data cube file and the raw data as well. So let me just open this data in another software package called Perclas Mira. Mira is one from our partners from Perclas in the Netherlands. I'm going to add some images to this project. Just going there. I'm doing this very quickly. So I'm adding 2 objects. So we have the images here, and let's now define 3 different classes. 1 class for the black part, 1 class for the white part, and 1 class for the red part in the image. So I'm going just to label a little bit within the image here and here. And also this is the red part. And then clicking on model search. So from there, based on this input information from the labeling, the software is trying to find a classification solution very quickly based on different machine learning techniques, also applied to this other example. We can also recheck that and relabel at certain levels, but this is already looking pretty good. Let's do here some adjustments as well. So quite much more training data, retrain the model. And once we find that the image is good, oh, that is not good. Let me just fix that here as well. Retrain. Oh, no, I made it bad. I'm afraid. But yeah, let me just delete these labels again. That's also easily doable to fix that very quickly. So once I found a classification solution, I can just take this classifier. Oh, this has been worse as well. Let me also delete this one. So retrain the model. I really made it worse. Let me just redo it. I think this is the demonstration effect. So let me just reload it here. These two. Open. 3 classes. Zooming in. 1 class for the background. 1 class for the for the white part in the image, which is this one, and this one, and 1 class for the red part. So model search again, somehow not perfect, but yet already good enough to provide us a qualitative statement. Yeah, this is getting better. So in the end, we can take this classification solution, and typically you invest more than 10 seconds like I do, export it as Cubert plugin, and just place it in the right folder. Let's call it Mira. I'm going back to the live view, refreshing the view mode here, and then I have it available. So let's go back to our example with this one. We can now apply this classifier in the live view. So this really is helping you to identify in real time spectral features. As said, this spectral classification solution is definitely not perfect, but typically, as I said, you would invest more than 10 seconds to find a proper solution, and you have full control of to set that differently. So I think this shows very nice the features of it. And let's take another image like this one. And also speaking of export features, I just go to this landscape symbol, open one image here, or can also use all of them, and just export them. Let's say we want to have it in NV file, which is good. So exporting it. And what we also gain now is this exported data file with all the media information that is necessary. So meaning we have information: when has the image been acquired, what was the camera that it has been used, what was the integration time, what are the dimensions of the data cube, which is super important if you want to import it into your own analysis tools. So with this NV file, this is easily doable. And that's just one of the features. And last but not least, I also would like to show you, going back to the live mode, that you can also use the video mode. Let's go to color infrared. That's also very nice. Let's make a new folder to store this. So going there, video. And if I press the red button right now, the camera is taking images set to the current set frame rate accordingly. So no image is lost. And this is super helpful if you have critical time-critical processes. So let's stop it again. Let's see what has happened. Taking a look at this new video folder, we just see that a lot of images have been recorded right away. So 5 Hertz means 5 entire data cubes per second. No data is lost. Anything can work. And with that, I want to close my presentation today. I really hope this gave you a good insight to see of what is possible. Thank you very much for your attention. And if you have questions, please do not hesitate to contact either any one of us or our colleagues in Japan as well. Thank you very much.
Okay, Marcel, thank you very much for your time.
You're very welcome.
以上で、本日の、プレゼンテーションの方を終了させていただきます。実際の先ほど見ていただいたこのカメラですけれども、弊社のブースで J の38番、こちらの方に実際のカメラの方とデモも実際できますので、小さい先ほどのカメラと X20 というタイプですね、こちらの方が置いてありますので、ぜひご覧いただければと思います。その場では、ご質問等ございましたらですね、弊社の営業担当等がありますので、ご回答させていただければと思います。本日はありがとうございました。Okay, thank you very much for time.
All right, thank you, Mazen.
Can you hear that?
No?
No, you couldn't. Okay, anyway, so we have lots of people here and I was listening to you.
I see. So if there are questions, you have to translate them so that I can hear them as well and answer them.
Yeah, but it's the time to go, so it's
yes.
already done. So we will take care. And I told you that we are some camera will be in our booth, and we will show them to explain. So in case if you get more questions, I will ask you.
Of course, just give me a call if needed, and I'm available.
Okay, thank you very much.
Thank you, Mazen. Thank
you.
you.
Bye.
Bye now.